Welcome to the Hawaiian island chain, one of the most isolated places on Earth. It is a deeply fascinating place, home to some of the most diverse ecosystems in the world, from lush rainforests to beautiful beaches to active volcanoes and frozen tundras. But how did people find this amazing place that's nearly 3,000 kilometers from the nearest continent? Western science has long thought that the Hawaiian Islands became populated by sailors drifting off course. However, these perspectives didn't fully understand the depth of knowledge of the skies of the original Polynesian voyagers. In the centuries following European contact and the overthrow of the Hawaiian monarchy, Hawaiian language and culture have been suppressed in many ways, including through legal action. In the 1970s, however, a Hawaiian Renaissance sought to revitalize the Hawaiian language and culture, including Polynesian wayfinding, the traditional practice of using the stars, currents, and animals to navigate across vast expanses of ocean. Built following the tradition of the ancient Hawaiian waʻa kaulua, or double-hulled voyaging canoe, the Hōkūleʻa made her first voyage to Tahiti in the mid-1970s. Navigated by Mau Pi'alung, who would later train Nainoa Thompson and Kalepa Baibayan in the traditional practice of Polynesian wayfinding. Both of these pioneers were lead navigators in the Malama Honua worldwide voyage, in which the Hōkūleʻa and her sister ship, the Hikianalia, circumnavigated the globe without the use of navigational instruments. The Hōkūleʻa is named after a star that passes just overhead at Hawaii's latitude during the summer months in the northern hemisphere. Hōkūleʻa, also known as Arcturus, is a zenith star. Looking up at the night sky, we see a dome of stars, planets, and other objects. Early astronomers looking at the sky envisioned that the Earth sat at the center of a fixed sphere of stars known as the celestial sphere. Though today we know this is not really the case. The stars that seem to lie on the sphere's surface are actually distributed in three-dimensional space. Imagine throwing a handful of pebbles on the ground. The view from where you might be standing is very different than if you kneeled down and looked at the pebbles edge-on, like our view of the stars projected onto the celestial sphere. But the celestial sphere has proven to be a useful model to help us think about the sky above, so it's still used today. Now, just like you can break a piece of paper up into grid lines along the horizontal, or x-axis, and the vertical, or y-axis, you can create a similar coordinate system in the night sky. At any point on Earth, or any other planet for that matter, you can divide your sky up into degrees of azimuth along your horizon from north, or 0 degrees azimuth, through east to south, measuring 180 degrees azimuth, and back to north again through west. The complementary coordinate, the altitude, is measured from 0 degrees at the horizon to 90 degrees at the zenith. Astronomers call this coordinate system the altitude-azimuth coordinate system, and the specific altitude and azimuth measurements for anything in the sky depend on the location, date, and time of the observation. Polynesian navigation requires a deep knowledge of the night sky, the ocean, the animal life found along the way, and a keen sense of observation. The original navigators and those on board the Hōkūleʻa and the Hikianalia understood how the stars move in the night sky from night to night, month to month, and across lines of latitude, using a conceptual tool called the star compass. Let's climb aboard the Hōkūleʻa and join it on its Malama Honua worldwide voyage to learn about how the sky changes. Now, humans love finding patterns, be it in clouds, or a night sky full of stars. Every culture on Earth has its own set of patterns that help them describe and understand the universe. In many of these cultures, star stories are an important way to record and relay information. As the Hōkūleʻa's crew travels south from Hawaiʻi to Aotearoa, also known as New Zealand, the navigators' keen eyes notice their sky changing. They find a familiar collection of stars, what we know of as the Pleiades. In Maori culture, this is known as matariki. This cluster of stars is visible from Aotearoa for most of the year, but sets for nearly a month in May. Just before dawn in June or July, matariki will once again rise, This is known as heliacal rising, marking the beginning of the new year and the first month of the Maori lunar calendar. From your own observations of the night sky, you may have noticed that the moon's phase, or how much of the face of the moon appears to be lit, and when it's visible in the sky, changes from night to night. This has to do with the orbit of the moon around the Earth and the relative positions of the Earth, moon, and sun. Believe it or not, half of the moon is always illuminated by the sun. You can test this for yourself if you have a ball, a pen, and a light source, like a flashlight or lamp. Take your ball, let's call it the moon, and hold it between your lamp and your head. You'll notice that none of the surface you can see is illuminated. This is the new moon. As you move your moon around your head, you see light hitting different parts of the moon, from waxing crescent to first quarter and waxing gibbous. You'll notice that the face of the moon is slowly getting brighter and brighter until your head is between your light and the moon, and the full face of the moon from our perspective is seeing light. This is the full moon. Moving back toward new moon, we again see the light hitting different parts of the moon, from waning gibbous to third quarter and waning crescent, and finally back to new moon. This cycle of phases repeats about once every 28 days and is the basis of the lunar calendar used by many people even today. You might also have noticed that the moon is sometimes visible during the day. Keep in mind that the stars are also still there during the day, but the bright scattering of sunlight in the atmosphere makes it so that we can't see them. But the moon is bright enough and close enough that it shines through. The difference between the rotation of the Earth on its axis and the orbital period of the moon around the Earth shifts the rising time of the moon by a little less than an hour each day. The new moon rises with the sun because it's between the Earth and the sun. After the new moon, the moon rises later and later, and its face becomes brighter and brighter until the full moon rises almost exactly when the sun sets, because it's positioned on the opposite side of the Earth from the sun. After new moon, look toward the eastern sky to find the moon rising before the sun sets. After full moon, look toward the western sky to see the moon setting after the sun rises. From Aotearoa, the Hōkūle'a sails around the northern side of Australia to Bali and on toward Africa. As they approach their destination, Cape Town, South Africa, the crew see a very similar sky to that in Aotearoa. This is because these two stops are at nearly the same line of latitude. Our perspective of the celestial sphere depends on our latitude. It only changes as we move north and south, along lines of longitude. Let's disembark from the Hōkūle'a for a moment and consider this familiar collection of stars. Some of you may know it as Orion, the hunter, who in the Greek tradition is destined to chase the scorpion, Scorpius, in the sky for eternity. For this experiment, let's also only consider locations along a single line of longitude, or a meridian. Let's start at Punta Arenas in Chile. If we observe Orion at 12 a.m. on the 12th of February, we see the hunter standing on his head in the northern part of the sky, with his bow pointing due west. On the same day, at the same time of night in Moquegua, Peru, the bulk of Orion is still in the northern sky, but is nearly horizontal and almost straddling the east-west meridian, or the line that connects due east on the horizon, through the zenith, and back down to due west on the horizon. Looking at the sky at the same time on the same night from Ellesmere Island in Nunavut, Canada, Orion can be seen standing upright in the southern part of the sky, with most of his legs below the horizon. We've just seen that the view we have of the night sky depends on our latitude on Earth. Back on the Hōkūle'a, the crew travels around the southernmost point of Africa. The Hōkūle'a is sailing to Brazil, still in the southern hemisphere, but much closer to the equator than Aotearoa. Now that we're Orion experts, I challenge you to try to see this group of stars the way the Tupi people of Brazil do, as an old man with a feather on his head holding a cane. Do you see him? Let's see where the old man goes throughout the year. We'll step through each month, keeping the day the same and the time the same. Starting on the 21st of January at 7 p.m., the old man is standing high in the northeastern sky. In February, he is almost exactly at the zenith. He moves from east to west, from month to month, along with all other stars in the sky until April, when he starts to move below the western horizon. By May, he is mostly below the horizon line, now visible on the other side of the planet. It's not until November that he starts to make his way back above the horizon, and in December he is fully visible in the evening sky. The Tupi people noticed this movement of the old man in the sky and used this moment in the latter half of December to mark the start of their rainy season in the northern part of what is now known as Brazil, and the beginning of the summer in the southern part. The constellations that are visible to us depend not only on the time of night and our latitude on Earth, but also the time of year. As we orbit the sun, we are exposed to different parts of the celestial sphere. Because of this motion, the constellations in our night sky change from month to month. The Tupi people and many other cultures across time and space used the yearly motions of the stars in the night sky to mark the seasons. But what causes the seasons? Contrary to what you may think, the seasons are not caused by a change in the distance between the Earth and the Sun, but rather are caused by the tilt of the Earth on its axis. The Earth rotates like a spinning top at an angle of 23.5 degrees. When the North Pole is pointed toward the Sun, the Northern Hemisphere gets more direct sunlight. It's summer in the Northern Hemisphere. When the North Pole is pointed away from the Sun, the Southern Hemisphere is getting those direct rays. It's now the Southern Hemisphere's turn for summer. It's winter in the Northern Hemisphere as the Hōkūle'a sails toward North America from Brazil. Back above the equator, they can again see the North Star, Polaris. This star has been used for navigation in many different contexts for centuries. In fact, it's understood by many that abolitionist Harriet Tubman led family, friends, and strangers northward, away from the horrors of chattel slavery, along the Underground Railroad by following the North Star. Polaris is different from the other stars. It appears to be fixed in the sky while all other stars travel around it. Just as Harriet Tubman did, if you follow Polaris, you'll be heading due north. The location of Polaris approximately marks the northern celestial pole, or the projection of the Earth's rotation axis onto the celestial sphere. As the Earth rotates from west to east on its axis, the celestial sphere appears to move from east to west. The apparent motion of the stars over the course of a night is due to the Earth's rotation. Looking at long exposure images of the night sky makes this motion very clear. From the northern hemisphere, we see the stars more or less revolving around Polaris. Stars that never set are called circumpolar stars and depend on your latitude. At the equator, perhaps near Natal, Brazil, the stars don't appear to move in circles, but rather stretched out arcs or straight lines from the eastern sky to the western sky. South of the equator, the stars appear to move as they do in the northern hemisphere, but there's no clearly visible south star like Polaris in the north. After setting sail from New York in the United States toward the final leg of its trip, the Hōkūle'a must pass through the Panama Canal. On its way, the Hōkūle'a sails near the Yucatan Peninsula, home to the ancient Mayan city of Chichen Itza. This settlement, iteratively built up between 750 and 900 CE, features structures that honor Venus, or Kukulkan. The main structure in Chichen Itza is the Pyramid of Kukulkan, also known as El Castillo. It rises 25 meters high with 4 large staircases placed at 45-degree angles, each with 91 steps. Together with the final platform at the top, makes a total of 365 steps, a reference to their solar calendar. The Mayan people were, and still are today, keen astronomers and tracked the motion of the sun very carefully throughout the year. As an important note, you should never look directly at the sun unless you have a special solar filter. If you don't, you risk severely hurting your eyes. The ancient Maya used shadow casting devices and special observatories to observe the sun safely, so you should too.
If you pay close attention, you might notice that the sun doesn't set in the same spot every day. The precise location of sunrise and sunset along the horizon moves throughout the year. For example, sunset moves from west-southwest on the December solstice to due west on the equinoxes to west-northwest on the June solstice. In fact, if we were to map out the position of the sun in the sky at the same time each day, we would see a pattern that looks like this. This figure 8 is a special shape called an analemma. This is caused by the Earth's slightly elliptical orbit around the sun and its 23.5-degree axial tilt that we learned about back in Brazil. If the Earth's axis were not tilted and its orbit were perfectly circular, then the sun would always appear in the same place at the same time of day at a given location on Earth. From carefully observing the sun, Mayan astronomers realized that the equinoxes were very special. On those days, the number of daytime and nighttime hours are the same. The Mayans were able to predict when the equinoxes would occur with such precision that on the March equinox of each year, the sun casts a slithering shadow down the side of the stair walls of the pyramid of Kukulkan, resembling the back of a snake, and attaching finally to the statue of a feathered serpent at the head of Kukulkan at the base of the stairway. At the time of Chichen Itza, this would have aligned exactly with the equinox, but today it's off by about an hour, and it's increasing in its difference day by day. In about 13,000 years, this phenomenon will be aligned with the September equinox, and in 26,000 years, it will return back to its original alignment. Remember we talked about the Earth rotating like a spinning top? If you tilt the top slightly off its axis, its handle traces out a circle. The Earth does the same thing. This is called precession and causes the equinoxes to change slowly throughout the years, decades, and centuries, and as a result, the location on the celestial sphere at which the celestial poles point changes. That means that Polaris hasn't always been and won't always be the North Star. Now safely through the Panama Canal, the Hōkūleʻa is on its way to Rapa Nui, sometimes called Easter Island, and part of the Polynesian Triangle, the area spanning Aotearoa, Hawaiʻi, and Rapa Nui, over which the original Polynesian voyagers traveled to explore new lands. From Rapa Nui, our ship sails to the center of the Polynesian Triangle, Tahiti. Along the way, the navigators track not only the motions of the sun, moon, and stars in the sky, but also the motion of the planets. From the Greek, this word literally means wanderers, but they were not the only people to realize that these celestial bodies move differently from stars. In the Hawaiian language, planets are known as Hōkūleʻa, literally traveling stars, or Hōkūleʻa, translating as wandering stars. All of the planets in our solar system orbit the sun in roughly the same plane. In our sky, this appears as a single line called the ecliptic, on which all the planets, the sun, and the moon travel. However, the planets are called wanderers because they sometimes wander with respect to the fixed background stars. This is a result of the relative motions of the other planets from our perspective on Earth. For example, imagine you and your best friend are running down the road. At first, you might both be going the same speed, but with a burst of energy, you go a little faster. From your perspective, your friend appears to be moving backwards. If your friend pushes hard to catch up with you and passes you, they'll appear to be moving forward again. The same phenomenon happens with planets in the sky because each planet orbits the sun at a different speed, passing us and lagging behind us at different moments along their paths. After a stop in Tahiti, the Hōkūleʻa and Hikianalia make their way back to Hawaii, bringing this 4-year journey to a close. Of course, this isn't the end for the Hōkūleʻa, nor her sister ship. In June 2022, the ships completed their Kealaikahiki voyage to Tahiti, featuring the first woman to captain a voyaging canoe along this path, Lehua Kamalu. That mission prepared the ships and crew alike for their next adventure, the Moana Nui Akea voyage, that will take both canoes on a 4-year journey to circumnavigate the Pacific Ocean. Now, I don't know about you, but after all this sailing and learning, I could really use some rest and relaxation. I've got my sunglasses, my towel, and my sunscreen, and I'm headed to the beach.